Okay. Hello, everyone. I'm Lynn Clark, and I make code cartoons. And I also work for Mozilla, where I've hacked on a few different browsers. Of course, we make Firefox, but we've also been experimenting with some other browsers. And one of these browsers is made using React. So as part of working on this browser, I figured out that I kind of needed to dig more deeply into how React works, because if you're working on a browser, you care about performance. So that meant stepping through the virtual DOM over and over and over and over and over again. And I figured as long as I'd spent all this time stepping through the virtual DOM, I might as well write it down and draw it out in cartoons so that you all could have the same benefits of having stepped through the virtual DOM over and over and over again without actually having to do it. So as I said, I'm going to be talking about the performance of the virtual DOM in this talk. And I should start by saying I'm not going to be talking about anything that you haven't heard before. So I'm going to be talking about things like keys and immutability and should component update. The reason I wanted to talk about them, though, is because I think that a lot of times we have this fuzzy understanding of the concepts around performance, and we don't really take time to bring these concepts into focus. So this means that we treat the knowledge as received knowledge. You just follow the recommendations like should component update because somebody who's smarter than you, somebody who you perceive as smarter than you because they're on a stage talking at you, told you to. But not all recommendations work in all situations. So I want to bring these concepts into focus so that you can have a better understanding of when you might use these recommendations and why. I should also say before I start that I'm going to be focusing on a very specific part of performance in React. I'm going to be focusing on the performance of the render cycle. So there are other things you can do to make React fast. If you're working in production, use the production version of React. That's a big one. And a lot of people don't realize that. But I'm not going to be talking about those little tricks. So this talk's going to go a little something like this. First, I'm going to talk about the basics of rendering in the browser and where it can be slow there. And then I'm going to talk about how you can minimize and batch DOM changes with the virtual DOM to make things a little bit faster. And then I'm going to talk about what tools React gives you to make things even more fast than that. So let's start with number one. And this is how the browser builds your web page. And you can kind of think of this in the same way that you built the web page to start with. You had this work that took place over time, and there was this initial period of work. So for React, this is the initial render. For you, this would be the initial work before the launch. And then you have subsequent bits of work that happen in updates. To extend this metaphor, your code is kind of like the project lead. It's planning the project and telling folks what to do to make this website show up. Unfortunately for your code, it only has one worker, only one person working on this project with it. And that's the main thread. So the main thread is kind of like a full stack developer, takes care of JavaScript, the DOM, layout, everything across the stack. And just as when you're working on a project in real life, if you only have one person doing the actual work, you want to limit what you're telling this one person, this one worker, to do. But before we know how to reduce the amount of work that we're asking the main thread to do, we need to know a little bit more about the work that it actually is doing. So as I mentioned before, the main thread is in charge of JavaScript, the DOM, and layout. So JavaScript, that's where your code lives. That's where you have functions, you're calling functions. The DOM is how those functions can tell the browser what changes it needs to make to the page. So basically, the DOM gives you these set of objects that your code can move around and add properties to in order to instruct the browser what the page should change to be. And the way that this works is that there's something behind the scenes called the render tree. So the main thread combines the DOM with the CSS model, and it creates the render tree. And from there, it figures out this thing called the box model, and that's what it passes off to the thing that actually paints the pixels on the page. This whole process is called a reflow, and that computation can take a little bit of time, especially if there's layout involved. So the main thread doesn't do that with every single change to the DOM. If it did, it would be spending most of its time calculating this layout. Instead, what it tries to do is batch as many of these changes as possible into the same group. So let's say that our code wants to change a class name on a button. It would tell the main thread to do that, go over and do it, and then add a div, go over and do it, make that change in the DOM, and then add another button. It would go over and make that change in the DOM. You'll notice that it hasn't gone over to the render tree. What it would have done, would have, on the first change, scheduled a recalculation, but it wouldn't actually have taken care of that. It's only when that scheduled recalculation hits that it then goes over and makes those changes in the render tree altogether. So we want to reduce the amount of work that this main thread has to do. And you might have figured out 2 different ways that you can do it. You could reduce the number of times that you're sending it over to the DOM to make changes in the DOM tree. And you can do these two things together, you could batch those changes in time so that it can batch its work better and only go over to the render tree once for a set of changes. So this is what React helps you to do just out of the box with the virtual DOM. Now I want to say React is not the only way to do this, and the virtual DOM is not the only way to do this. These ideas have been around since well before React. So you can get as good or better performance with vanilla.js as you can with React or with a virtual DOM. It's not necessarily that React is faster than vanilla. The thing is though, in order to get that performance, your code has to be smart. So your code needs to know how to direct the main thread pretty precisely in order to do these things quickly. To go back to the metaphor, your code needs to be both a really, really good product manager. It needs to know what to show to the user. And it also needs to know how to be a good tech lead. It needs to know how to ship those things quickly. Of course, your code is only as smart as you make it, so that means that all of the developers on your team have to have a really solid grasp of all of those concepts and also not make too many mistakes. What React does for you is it offloads this work. So it's kind of like your code brings in a consultant to do all of the tech lead work. And that frees up your code just to be a good product manager, just to focus on what it needs to ship, not on how to ship it. So let's take a look at how these two, React and your code, work together to direct the main thread in shipping this website. And I'm not going to be showing you the main thread through the rest of the slides. You can just assume wherever work is being done, the main thread is there doing the work. So this brings us to part 2. How React minimizes work using the virtual DOM. And in order to show this, to demonstrate this, I'm going to use an example. In this example, we have a list of numbers. When you click the button there, it's going to multiply those numbers by themselves, so it's going to square those numbers. Let's walk through the initial render of this. I'm going to start from the very beginning. Your user has downloaded some HTML. It's been parsed, and there's a container in there. So the container is just the HTML element that you're going to insert your React app into. At this point, React has been loaded, and so is your code. And along with your code, these things called components have been loaded. And these are basically deputy product managers. They know what a specific part of the page should look like. And we're going to start looking at this code. So React DOM.render. And then we pass in a list element and the container. Now we've already talked about the container. What's this list element that we're going to be passing in? What's a React element? A React element is a way for your code to hand off the requirements to its tech lead, for it to hand off the requirements to React. So it's kind of like a little note card that your code writes down these requirements on. It has a type, which is the component that's going to be used to build the thing. It has the props and the children. And React's going to hold on to this element. It's just going to tuck this note card in its pocket until it's ready to build the thing. And the thing that it builds using these requirements is an instance of the component. So that's the thing when you call this.setState, you're actually interacting with the instance there. It has refs. It is what React uses to hold on to the connection to the DOM that's actually using to change things. But you don't have to manage the instance itself. You don't create it. You don't have to destroy it. You are just in charge of working with elements and telling React what to do, and it manages the instances for you. So your code asks for an element. This is the list element that React creates. And then your code tells React to start rendering that element into the container. And this begins the construction of React's internal render tree. Now, if you don't follow, this is being recorded. It has been recorded before, so I'm gonna have to move through it quickly, but you can always go back to this later and look more closely at this algorithm. And if you want a version of this that you can zoom in on and click around, check out Code Cartoons on Twitter. It's up there. Before I start stepping through, I should also say this algorithm has changed. It actually changed since I started writing this talk, and it will change again. They're working on some performance improvements, major performance improvements, and so this algorithm may not be the same in the future, but for today, this is how it works. So React starts by creating the top-level wrapper, and it's just an implementation detail. This just makes things easier for React to manage, but this might change soon. Then it goes and creates an instance of that top-level wrapper. And it has wired up this instance so that when you call render on it, it's going to render to the list that we passed in. So it's going to create an instance of that list element, set the props and states, and then it wants to create the corresponding DOM for this list, but it doesn't know how. So if list were a div, if this were a div instead of list, it would know. It has internally defined components like div that it knows how to render to. But since this is not one of those, it's going to have to ask. So it asks list, what should I render for you? And so list gives it a big list of things. List responds that, okay, I need a button element, and then for each thing in the this.state.items array, create an item element for me. And then wrap all of those inside of a div element. Create that for me too. So React creates those elements, tucks them away, doesn't really care about them, except for the wrapping div. That one is going to pull out and actually start creating the instance for it. And then because it's a div, it does know how to create the DOM. So it goes over to the DOM and creates the div and the DOM for it. Now note, it did not make that div a child of the container, because that would have scheduled that reflow. But we want to make all of the DOM nodes before we schedule that reflow. So now it needs to create instances for all of the children of this div. And for this, it's going to go from a complex structure to a simple structure. So it has this array with a nested array that represents the children. It's going to turn that into an object. And to reflect this structure, it's going to use property names that have kind of a complex structure. So the button is .0 because that was the 0th item in that containing array. And then the items themselves, they're .1, .0, .1, .1. That reflects their position not just in the top level array, but also the second level array. So React takes this flattened list and creates the instances for those. And now it's time to make the DOM elements. Button's easy. It knows what a button is, so it goes over and makes the button. But then it gets to the first item, and it has to ask. So it asks the item, and the item says, okay, create a div element for me. And for the prop that was pushed in to me, go ahead and make that the text content of that div element. So it makes the element and the instance, and because this is a div, it knows how to go over and make that in the DOM. And so it does this 2 more times to get the full list. And now that we have all of these DOM nodes, it can connect those children up to their parent, to the wrapping div, and connect that up to the container. And this is what triggers that reflow. So we get our UI, and that's the initial render. Now the UI is ready for the user to interact with it. It's ready to actually do those updates, to make those changes in the UI. So let's see how the virtual DOM handles that. We're going to click the button and see what happens here. So React figures out the onClick handler for the click. It does it using something called event delegation. I don't have time to go into that, unfortunately, but there is an explanation in React's docs. So it figures out what handler it needs to call. It calls the handler. And the handler would be code like this. You know, you get the list of items from the state, you set it to a new variable, then you perform operations, and then call setState with the items. And if you think that you see a possible bug in this, we're going to get to that later. So this handler would have been bound to the list instance. That's how React knows which instance in its tree it needs to call setState on. So what happens when setState is called on the list? React doesn't immediately handle the state change. It uses a few different queues to handle this. It takes the partial state that was passed in for the list and puts that on a queue on the list of partial state updates. And then it takes that whole list instance and puts that on another queue called the dirty components array. So it's going to do all that queuing and then make sure that no other changes have been added by other things that have been on this click handler. You know, because you could call this.setState on multiple instances in the click handler. Once it's figured out that it has all its changes, it goes through and flushes the queue. So we only have one instance in the queue. We're only going to update one thing. We start with the instance that had setState called on it, the list, and work down from there. So I'm going to gray out everything, all the work in the initial render. It doesn't get rid of this. It actually holds on to this to make comparisons, but this will make it clearer as I'm walking through what we're doing. So React calculates the next state and props and sets them on the instance. And then asks the list instance, now that you have this new state and props, what should you render to? And this creates the elements, the new versions of the elements. And from there, it updates the children instances and compares the previous instances to the new ones and figures out whether it needs to make DOM changes based on that. Now, the button didn't change, so it doesn't need to do anything to the DOM for the button. Then it gets to the first item. And again, because item is something that doesn't know how to render directly to the DOM, it has to ask the item, okay, now you have this new state and props, what do you render to? For the first item, remember 1 squared is just 1, so we haven't had any changes there. It realizes it doesn't need to make any changes to the DOM, so it just skips over making that change completely. Then it gets to the second item. 2 squared is 4, so that actually is going to change. So it makes the update, sees the change, goes over to the DOM, and makes that change. And then it does this once more for the third item. Because these changes happened in quick succession, they were probably handled in the same reflow. And that's how React makes them faster. So it figures out the smallest number of changes that it needs to make to the DOM, and then it batches them together so that the browser can do a smaller number of reflows and layouts. But there's still a good amount of work happening here. So how can we reduce this work further? This is where we get to the third part of the talk. What little tricks you can use to make React faster. And the first one is one that you probably already know, because React shouts at you if you don't do it. Whenever you're creating an array of children using something like map, it's going to tell you that you should be using keys. So I want to show you why using keys can help performance. For this, I'm going to need to switch up my example to something that really highlights this. And it's a sortable list. So when you click reverse order, it's going to take these things that were, these fruits that were sorted alphabetically and make it reverse alphabetical order. And I'm just going to jump ahead to the setState process. This is where it gets interesting in this whole interaction. So this is where React is dealing with the children of that div. You'll remember we flattened them and then gave names to each of the children. And from that, we looked at the instances, what old instances and what new instances were different. So we made that comparison between the old, the previous, and the new instances. Let's take a closer look at how React does that. So what it does is it just takes the key, the property name, from the previous and the new ones, and takes whatever object's there and compares them. But as you'll remember, the name is just derived from the array indexes. And we've reversed the order, so they all have different indexes. That means that React is comparing apples to oranges, quite literally in this case. Apple was at position 0 before, and now orange is. So when it compares these two lists, it thinks it needs to update the values of all of the items, except for the middle one, because they all look different than they used to. Now let's say that we had given React meaningful keys, something like the actual fruit name. The key would then be used in the name, so it would be .1.orange, and React could dig into the previous and next items and figure out which ones actually matched. And it would see that nothing's changed besides the order. So it would know that it could just reorder the DOM elements. Now in this case, it's not a huge difference. But just imagine if each of these items in this list was a complex DOM structure with lots of nodes beneath it. That could be a real time savings. But it's only really a time savings if your list is going to be reordered, if those array indexes are going to change. So if you're doing something like reversing the list or taking items off the top of the list. If you aren't changing the order, then there's no performance impact here. And this is one of the reasons why it's important to understand the why behind a recommendation, because recommendations don't always have the same impacts across different use cases. So let's look at a use case where keys wouldn't have much of an impact, but another trick would. So it's a list where new items are being fetched from a server and added to the end of the list. So let's say the user pushes the button, but there are no new messages. React is going to go through the process of building out creating all these elements, updating the instances, even though nothing needs to change in the DOM. So this is something called wasted time, and you can see it if you use React perf tools. How can you avoid wasting time like this? I'm sure you've heard of one way, and that is should component update. So the way this works is when the user clicks and this .setState is called, before building up the render tree below the list, React will ask the component a question. It will say, if I give you this next props and next state, do you even need to update? And if the component says, no, I'm good, then React doesn't call render and it doesn't do anything else to that component or to its children unless the child has setState called on it. But in this pass, it doesn't do anything to the children. So this is great because we can skip computing the list and everything under it. So we save a good amount of work here. If you were looking closely at this should component update though, you might have noticed a potential bug. And this ties into that other potential bug that I mentioned earlier when we were looking at the click handler. So it depends on how you're updating the state, whether or not this is a bug. Let's say you're updating it this way. So you set that new variable next items to this .state.items, and you push your new item onto the array. And then you call setState with that new variable. What would happen here is that you would never see the new items. They'd never show up in your UI. Your should component update would always return false. Why is this? It's because even though you have two names for this thing, both names still point to the same thing. So they're equal because they're just different names for the exact same thing. When you do an equals check in JavaScript, it's just going to check if those things are referring to the same object. So even if you make a change, that should component update is going to think that the old state and the new state are the same thing. So it's not going to see the change. Now you could make it so that next state is always its own object, or next items is always its own object. And then your should component update would see that the previous items variable and the next variable are different. Now the problem is it would always think that they had changed, even if it hadn't. So it would never return false and not give you any performance improvement. Now we could do a deep equality check in our should component update where we compare the actual values. But depending on how heavy that check is, it might actually take you more time. So it'd be nice to have that simple, quick equality check, but still catch changes to the data. And this is what immutability can do for you. With immutable data, if two variables are pointing to the same object, they have the same reference, you know that the data hasn't changed. If it does need to change, then you create the new object. So if you're using immutable data, then you can do these quick equality checks, which are pretty fast, in should component update. And that can save you this work below where you call this.setState. But what if the change happens lower down in the tree? What if it happens in one of the children of list? Do you still need to compute the whole thing to catch that change lower in this tree? Let's walk through that case. So a good example of one of these kinds of lists is a to-do list. When you click on a to-do in a to-do list, that to-do is changing, but the other ones aren't really, and the list itself isn't really changing either. So how can you avoid doing work for the whole list when only one item is changing? When you're using vanilla React with local component state, this can be pretty easy. All you do is restructure your state so that you can call this.setState lower in the tree on the item itself. But when you're using something like Redux, this can be harder to do. And that's because you're firing off actions, and then the state, the updated state, is coming in through connect. And that's usually at the top of the tree. However, there is a way to do that. And it's by calling connect lower on the items itself, on the items themselves. If you want to do this, though, you'll probably need to rethink how you're handling your data for this to work. Because you'd have a component structure like this, and a lot of people would pass in the full array of items into the list and then pass each item down to the item. But if you want to update any one of these items, you don't just change it in the item that's being updated, you have to change it in that array. So the list is going to think that it needs to update as well, because this is a different object than it was before. Now, if you just pass in the ID, nothing at the list level needs to change. You just pass down that ID, and from map state to props in Redux, you can go from the ID to the item. So then, when the item changes, you only see the new object in the affected item. You only trigger the re-render on that item itself. Now, one thing to watch out for here is that the way that Redux works, you do end up adding a listener for each of these items in that case. So this performance hack might work, it might not. This is why you want to test. And this is how you can save work on higher levels or sibling levels of the tree. So I wish I had time to cover other performance tricks, things like memoization and virtualization, the new incremental rendering algorithm, or how you can use observables like Evan was talking about yesterday, which make things like MobX and Relay, it makes it possible for them to notify components of changes. But this is going to have to be it for now. So here are the techniques that we did cover. We talked about how you can use keys to help React match previous and next instances. We also talked about using should component update to short circuit work lower in the tree and how immutability can factor into that. And then we talked about how you can use set state or connect lower in the tree so you can save work higher in the tree. I hope this has given you a good overview of some starting points for working on performance in React. As you can see, there are lots of tweaks that you can make. Some of them are right for certain cases, some for others, and some will actually have negative impacts if used in the wrong use cases. This is why people say to measure, to benchmark things. And hopefully, this talk has given you a good framework for understanding what it is that you're measuring. If you want to learn more, you can check out codecartoons.com or Code Cartoons on Twitter. I'm going to be publishing this as an article in Smashing Magazine pretty soon. So you can follow along there to see when that gets posted or sign up for my mailing list. And thank you very much. Thank you.